The recovered Flaperon is a mechanical record. Analyzing its failure reveals the forces from its final moments. We see a structural paradox, a sharp line where the forward structure remains entirely intact, while the trailing edge is completely sheared away. This damage profile suggests a very specific sequence of events. It requires an exact end-of-flight trajectory to produce this kind of localized fracture. We're going to test 3 competing force models against this exact fracture line to see which one accounts for the physical reality. First, the official high-speed spiral descent. Second, the independent controlled ditching hypothesis. Third, anomalous external force theories. Ultimately, a proposed theory doesn't matter at all if it cannot mathematically satisfy the physical reality of these localized fracture lines. To ground this forensic analysis, we've got to establish the baseline physical architecture of the component. The Flaperon uses a composite construction. If we peel back the layered shell of carbon fiber reinforced plastic, we find an internal aluminum honeycomb core designed for high rigidity and low weight. The component anchors to the main wing at these forward attachment hinges. During normal flight, aerodynamic load paths distribute stress safely across these specific hinges. To catastrophically delaminate this composite matrix, you need extreme shear force that bypasses those standard loads. Delamination failure modes in solid mechanics are complex. They happen when internal layers separate because forces are applied perpendicularly to the material's grain. Shearing this composite requires directional force vectors that bypass the strongest points of the structure and focus on the trailing edge. A valid theory has to isolate enough force to tear the trailing edge while leaving the attachment pivots firmly in place. We'll start with the official high-speed water impact hypothesis. This model is the basis for the conclusions found in the official safety investigation report. This scenario involves a high Mach spiral descent into a flat surface. In this model, we see heavy red force arrows accumulating on the leading wing edges. The aerodynamic flutter hypothesis suggests the structure began failing midair. It proposes that rapid oscillating vibrations created micro-stress fractures across the surface before the plane hit the water. However, flutter forces are violent and multidirectional. Mathematically, these forces would likely snap the hinges before the trailing edge could tear away. We also have to consider the hydrodynamic shock of entering the water at terminal velocity. High-speed impacts involve a massive transfer of kinetic energy. We've got to reconcile how this component survived in large fragments if the surrounding airframe was subjected to forces that pulverized lighter structural elements. A catastrophic vertical fit would usually shatter the entire carbon matrix simultaneously, rather than tearing off a specific section. When we look at the jagged edges of the recovered debris, we're seeing localized tearing that's difficult to produce in a total airframe destruction scenario. The high-speed spiral model struggles to produce a neatly localized trailing edge tear without obliterating the entire component. Now we'll analyze the controlled ditching hypothesis. This model requires a low-speed glide with the flaps fully deployed into the water. This creates unique load paths. Blue drag force arrows show the water pushing upward specifically against the trailing edge of the deployed Flaperon. The water drag creates a lever action. The force acts exclusively on the extended trailing flap, while the forward hinge stays anchored in the wing. This upward pressure causes the composite matrix to snap. It mechanically isolates the damage, which explains why the leading edge remains intact. This deployed shear pattern matches the forensic baseline we see in the recovered debris. We also have to acknowledge that a ditching maneuver in open ocean swells is extremely difficult to execute. While it's a difficult maneuver, the ditching kinematics are a match for the upward delamination we physically observe. We'll now look at the anomalous and external force models found in independent research. These discussions often involve unverified thermal footage and non-standard kinetic events. Every claim has to be filtered through the requirements of fracture mechanics. If we're ruling out water impact, we've got to identify the physical forces capable of shearing a carbon fiber trailing edge in midair. Carbon fiber reinforced plastic and aluminum honeycomb have specific thermal degradation thresholds. High heat exposure causes these materials to boil, carbonize, and eventually disintegrate at a microscopic level. This microscopic view reveals clean physical fracture nodes. There's a total absence of any burn or melt indicators on the recovered debris. This lack of heat damage rules out theories involving conventional explosions or extreme thermal events. This absence of thermal evidence dictates the requirements for any forensic analysis. If a model doesn't account for these microscopic physical constraints, it can't accurately describe the event. The physical evidence limits any anomalous theory to pure cold kinetic forces, because extreme thermal exposure simply didn't happen. We can now build a final matrix using this forensic data to compare how each model performs against the physical constraints. The high-speed spiral fails the fracture match because it can't easily produce that localized trailing edge tear. The ditching model gets a passing indicator for the fracture match, as the kinematics align with the upward delamination we see. The anomalous force models are limited by the thermal constraint, as the material shows no sign of heat exposure. It's important to remember that we can't extrapolate an entire global flight path from a single localized mechanical failure. But the localized damage on the Flaperon is clear about one thing: it strictly requires a specific directional load vector. True independent research avoids unconstrained speculation, remaining anchored entirely in the laws of fracture mechanics.